Okay, so we're going to continue on the arithmetic instructions. Well, that was out of date. All arithmetic instructions set flags, and including carry flag, overflow flag, zero flag, sign flag, parity flag, and auxiliary flag. And those flag bits are stored in flags register. The usage of these flag bits are mostly for conditional branch instructions. Yeah.
Do they each have a specific location
Yep.
in the register?
That's right. So remember in the E flag register we have 32-bit,
Right.
and if you count, we only have 6 of these arithmetic related flags. So these bits will be taken specific bits from that register, and some other bits are unused. But every flag has a bit in that register. We have 3 kinds of addition instructions: the plain addition, addition with carry bit, and then increment. First 2 addition instructions take destination and source as the operands, and for the increment, it has only one operand. Similarly, subtraction instructions have a few variants in the format. Subtraction D, S, that's the plain subtraction. And remember, we're subtracting source from destination. It's not the other way around. And subtraction with borrow SBB, and not only subtract source from destination, it also subtract carry flag from the result. Then we have decrement, which is D minus 1, and then we have negate, which will take the opposite number and into complement. All right, let's look at some examples. Assume that we have these initial values in the registers AX and BL. AX is a 16-bit register. We have 1, 2, 3, 4 hexadecimal, and in BL we have A, B. And in memory location sum, we have this word 00CD. So we're not specifying the segment base, but by default we know it's DS. And we're saying at effective address sum, which is in fact a constant number, we just use these to represent this number because we don't really care what the number is. We just know that at this location memory DS colon sum, we have a word 00CD. Now, if you don't follow what I just said, I said at this memory location DS colon sum, we have this word 00CD. But you have to imagine the memory map. We do have these individual bytes there. The reason we have 00CD as a word is because we have CD, that byte stored at DS colon sum, and then 00 stored at memory location DS sum plus 1. Right? Because the little endian, the most significant byte is stored at higher address, and the least significant byte is stored at lower address. Okay. The problem here is to show the results of each step of the following instruction sequences. ADD AX, comma, bracket sum, and then followed by ADC BL, comma, 05, then negate BL sum sub AX, comma, 12H, increment word pointer. Okay. Do you want to take a few minutes to work on this? Now, just a hint that we're talking about following instruction sequence. So these instructions will be executed one after another as like a part of the program. So that is to say, we first execute ADD instruction, which will update the carry flag. And the reason we say that is the next instruction, ADC, is gonna use that carry flag bits. All right, so let's look at how these instructions are going to be executed. First instruction is ADDAX, comma, bracket sum. And this is a plain ADD instruction. And it has two operands. The source is the sum, destination is AX. And sum here is the memory operand. So we're going to read the word from memory at location ds colon sum, and that's the meaning of this parenthesis here. We just want to use this notation to indicate that's going to be getting the content from memory at location ds colon sum, and then we're going to add that value to the value of AX. So that is 00CD plus 1234, both in hexadecimal. And the sum of these two numbers is 1301 in hexadecimal. And during the addition, there's no carry bit generated from the most significant bit. So this ADD instruction will set carry flag as 0 because there's no carry bit generated. If there is, then that carry bit should be a 1. Also, it's going to store the sum into the destination operand, which is AX. So AX will have 1301 in hexadecimal. The next instruction, ADC BL, 05. ADC is to add with carry bit. So we'll add these two numbers, BL, the content of BL, with this immediate value, this is 05, and with this carry flag, the value of this carry flag. Because its previous instruction, this ADD instruction, generates no carry bit, so CF is 0. So this ADC instruction will have a 0 here for the carry flag, so the sum will be just AB, which is the value of BL, plus 05, plus this 0. So the final result for the sum is B0 in hexadecimal. We're going to assign this B0 into BL. And this carry flag will be also updated because there's no carry flag generated. So CF will again be a 0. Remember, all these instructions will update these carry flags.
What is IMUL?
This immediate 8. So it's an immediate number, it's a constant number, 8-bit. And we say this because BL is an 8-bit register. Right? And 05 is one of the immediate 8-bit number. Next instruction is negate. So negate will take the operand. Here we have only one operand. Take the operand, multiply with -1. Let's get the opposite, to get the negated value of the original value. So the operation is to do the negation on BL and put the value back to BL. Because after the second instruction, BL has B0 in hexadecimal. So we're going to take this B0 hexadecimal, we're going to do the negation. B0 is this number, okay, in binary. Okay? This is B, this is 0 in binary. And we're going to do the negation. So actually the negation is, again, you're going to invert the whole thing, then plus 1. Yes, taking the two's complement. So it's going to be 5-0 at the end. Yep.
Isn't that BLAB?
BL was AB before we do ADC.
Alright, so after we have after BL changed to B0, you're gonna keep using the final B0?
Yeah, because this ADC BL, 05H. Remember, this is the destination. This operand is supposed to have the final result. We're going to update it. Okay? That's the meaning of the destination. So whatever final result will be loaded, will be stored into the destination operand. Next instruction is subtraction. We're going to subtract AX, 12 in hexadecimal. So which one is source, which one is destination? AX is destination, 12 in hexadecimal is the source. And we're going to do the subtraction by subtracting source from the destination. So it's AX minus 12 hexadecimal. We're going to take this, 1201, 1301. Again, AX now has the updated value, oh, I guess the confusion came from whether these instructions are independent or these are part of the program. So we said at the beginning that all these instructions are part of the program, so they are executed one by one. So the previous instruction will affect later instructions. And when we do this case, 1201 minus 0012, because there's no carry bit, or no bit need to be borrowed to perform this subtraction, so the AX will have the final difference of these two numbers, and the carry flag is a 0 because there's no bit borrowed from the top. Okay.
When the carry flag is gonna be
So one gonna be 1. That's when, for example, if you are subtracting, let's say 0012 subtract 1301. As you can see, if you do the subtraction, you're gonna be borrowing a bit from the 16th bit and then form the subtraction. So in that case, the carry flag will be set to 1. So for addition is to look at whether a bit is generated over the most significant bit. For subtraction, you basically look at whether a bit is borrowed or not. Next instruction is the increment. Now, for this instruction, it's a little bit tricky here in the sense that you need to specify the data size of the bracket sum. If you just say increment bracket sum and in bracket, that's going to cause confusion to the microprocessor. Because if you just list this bracket sum, it could refer to a byte or a word or a double word. There's no other registers used in this instruction, so there's no way to tell exactly how many bytes this increment operation should be working on. So that's the reason we have this extra prefix, this word pointer, to say that, okay, this increment instruction is going to do the incrementation on a word, and that word is stored at ds :sum. So what we're doing here is we're going to read the value from memory location ds :sum. We take the word, then +1 because we're doing increment. So this 00CD, which is the original value, will be read out of the memory. Then +1 is the sum of these two numbers, and then we're going to put this new value into the memory location at ds :sum. Okay, my follow-up question or something I can ask is if I want you to draw the memory map, what we're going to see a memory map. This is ds sum, and this is ds sum +1. Okay, I'm gonna probably ask you to put in the updated values into this box. We know at that memory location, ds sum, we have an updated value that is 00CE. So it's going to be 00CE. Okay? Because this instruction, this is the increment, and the destination operand is the memory bracket sum. So that means whatever operation you did, that is increment, the updated value should be stored back into the memory because it is the destination.
The sum is two bytes. So why you have a just 1 byte in there?
So ds sum, again, ds is the destination, is the data segment. Sum is a number, okay? And this number is the effective address. Okay? So let's say you can replace the sum with 1, 2, 3, 4. That's the address. What is the next address? It's going to be sum plus 1. Okay? And using this memory map, we know that at this location, this is a byte. The next location is another byte. The minimal addressable unit for the memory is a byte. So this sum refers to this byte. Sum plus 1 refers to this byte. When we say we want a word from this address, that means we're going to, start from here, take 2 bytes. These 2 bytes will make up the word. But what word? That's 00CE, because we're, again, using little endian, so this is the most significant byte, and this is the least significant byte.
So that was even by pointer, we still have the same result, right? We just wouldn't be calling that here.
Very good question. If I change that instruction to increment byte pointer, right? We change this back to the original value, which is CD. If I do increment byte pointer sum, what will be the content in this memory?
But the
So we're going to do increment byte pointer sum. So it's going to be CE. Yes, it's the same. But the operation happen for this instruction is it's going to load this byte only. It's not going to load the other byte because we're talking about a byte pointer, and we're going to look at only this byte, and we're going to increment, then we're going to put the value back into this location. Any other questions? All right, multiplication, division. These instructions can work on both signed and unsigned integer versions, and register A is always one of the sources. This is a little bit different from the previous addition subtractions. This register A, including EAX, AX, AH, AL, assumed to be one of the sources. Destination always the same. It's size dependent. There's exception. Sign multiplication does allow for a slightly different operation. The easiest way to evaluate these instructions to figure out decimal values of operands, do the operation in decimal, then figure out binary hex values of results. That's for you if you want to kind of sketch out what will be the outcome of these instructions. You can change them to decimal and do the multiplication, then change them back. Multiplication S, it's unsigned multiplication, and with IMUL, that is signed multiplication. Okay, so if we're doing, first of all, when you look at these instructions, they have only one operand, okay? Written together with the instruction is the source. We know that in order to do multiplication, we need 2 numbers, okay? And these multiplication will generate the product, which typically has more bits than the source. If you multiply with a 8-bit with 8-bit, you're expecting a 16-bit number as the product because of the range change for the multiplication. So what we're doing here is, for example, if it is a byte operand, the other source is assumed to be in AL, and the product is assumed to put into AX. Although AX and AL never showed up in the instruction itself. For the word, if the source is a word, we're going to use AX as the other operand, and we know the product will be a 32-bit number. The upper 16 is going to be in DX and lower 16 is going to be AX. For double word, it's going to be similar, so we're going to use EAX as the other operand, and we use EDX and EAX together to store the final product. Only carry bit and overflow flag will be updated. Division is similar. We have unsigned and signed divisions, and we're going to split into quotient and remainder. And the quotient will be stored in corresponding AL if the S is a byte, and then the remainder will be stored into AH. And similarly, we're going to use other registers to store the quotient and remainder for the division operations. Again, just let you know that we will not cover multiplication division in the exam. These are just for your information.
Any exam or just this company?
Any exam in this class. I'm sorry, I disappointed you. I can add it back.
No, it's okay.
You know what? I will add it back, especially for you.
Yeah.